so I think we'll move on to the next talk, which will be given by Philip Metzger. So take it away.
Okay, hello everybody. Thank you to Ryan and Addie and the other organizers. I wanted to start out with this picture from SpaceX showing the dust billowing during a hop of their water tower. And this is the dust that's being lifted off the edges of the concrete pad. There's actually a concrete pad under that rocket. And I want to show that to say that's not what happens on the moon. Like Jack mentioned, there's no billowing. So next chart, please. This picture from an artist shows, I gave input for this picture, and this shows what we know it really looks like. The dust is blowing in a very thin layer and at a very high velocity. When you look at the dust in the video, it doesn't look like that much dust, but that's because it's traveling at 3 kilometers per second. And so it's stretched out in space. And so the local quantity of dust it's not that concentrated. Next chart, please. So we get most of our information by doing computer simulations because we haven't had the right kind of instruments during a lunar landing yet. So, but we've got a fair amount of confidence in these simulations. In these simulations on the left is the rocket nozzle pointing down at the surface. In the top, you can see it's high density gas right under the nozzle where it's hitting the surface, and then it becomes lower density as it moves off to the right. On the bottom pane, it's low velocity right under the rocket nozzle, and then it speeds up to high velocity as it moves off to the right. And so this rocket exhaust is picking up grains off the surface and accelerating them in a thin sheet at very high velocity. Now, when you do experiments terrestrially, you typically get a crater right under the nozzle. And that's because of the difference of the terrestrial and the lunar environment. There are other mechanisms that can happen inside the soil where the gas shoves the soil down and causes it to shear or to compact locally under the nozzle, or the gas diffusing through the soil creates a distributed body force in the soil that causes it to shear. Typically a combination of these factors, and you can end up getting a crater which disrupts the flow field. Now that didn't happen in Apollo. That's not unexpected because the lunar soil is impermeable and frictional. But we don't know where the turn-on limit is. So with much larger landers in the future, there may be more of these localized effects under the nozzle. Next chart, please. Most of our data comes from looking out the window during the Apollo landings. Next chart. And there's a video. Can you start the video? Is it going to work?
I don't think so. The slides have been.
No, I guess we're not going to get. Okay, that's too bad. Let's go on to the next one. And I'm just going to have to describe the upcoming videos. Okay, so we can see rocks blowing, and we can calculate the velocity of the rocks from the videos, and they match what the simulations predict. We can also see the shadow of the rear foot pad in the image, and the shadow is distorted. The circular or elliptical shadow of the foot pad has been elongated to look like a cylinder, and that stretching is due to the thickness of the dust sheet. And from that, we've measured the angles that the dust particles are traveling, and those agree with the simulations as well, which helps to increase our confidence. Next chart. When you look under the nozzle after the landing, there's no crater, but there's a lot of indications of the erosion that took place. You can see headed erosional remnants, and there's some features that were misinterpreted during the Apollo program. In the next chart, please, we did field tests where we fired thrusters on volcanic tephra, and we had these weird phenomena occur, including strata that appeared in the crater when we fired a rocket on it. And those strata were the results of mechanical discontinuities in the natural tephra on the volcano. So when we go back to the Apollo landings, go to the next chart, please. We realize that some of these strata are visible in these images as well. Now the erosion, it was a higher rate away from the nozzle. Directly under the nozzle, the gas was low velocity. So the maximum erosion occurred about about a meter away from the center of the nozzle. And so you can see the soil is stepping downhill along this discontinuity. And this was Apollo 11, but next chart, please. This is Apollo 12. You can see the same thing. The nozzle is in the upper right corner. It's smoother terrain at the contact, and on the downhill, the stepping down side away from the nozzle, it's more cobbly because the next layer down has not been completely removed. So we can see features, and when we add up, let's go to the next chart, please. When you roughly, crudely quantify the effect of all these features, you can estimate that it was order of magnitude about a ton of soil that was blown. Next chart, please. Another effect that can be seen, Ryan Watkins did her dissertation and has published numerous papers on the photometric disturbance around the landing sites. And I think we can explain this now. Next chart. Okay, we can't show the video, but this video shows the ejector wraps all the way around the moon. And
hey Phil, we do have your videos if you want. We could either switch over to me or we could show them during the break, whichever you prefer.
I'm going to run out of time, so let's just keep going.
Okay.
But the video, the ejector wraps all the way around the moon, and there's no discontinuity at 75 meters like the photometric disturbance. Next chart. And this next video was going to show that at the orbit of the gateway, the ejecta sheet crosses that orbit. And when the gateway, NASA's proposed gateway, flies through the ejecta sheet, it's going to receive, best estimate, about 10,000 hypervelocity impacts per square meter. Now, these are 10 micron and finer particles at that altitude, so it's not going to be mission-ending damage, but it's something we need to account for in the environmental specification and the maintenance and the reliability of the hardware. Okay, next chart. Our best data comes from Surveyor. Apollo 12 landed 160 meters away. Next chart. The shadow from the bolt head that had been removed was etched by the sandblasting. There's also a shadow. You can see the left and right sides are different brightness. That was the shadow of a cable. It's not as sharp of a shadow because of the penumbra. Next chart. Which tells us the dust was not a point source. The left side is the paint that was protected under the washer. The right side was sandblasted. It's got dust mixed in. You can also see a crack running from the top left down towards the middle. Next chart shows how the paint got all cracked up, and there's pinholes in the paint. The pinholes are correlated to the locations of the junctures of the cracks. And those are where about 100 micron sand particles penetrated the paint. By looking at the optical density of the blowing dust, we can calculate, we know what the fraction of sand-sized particles are in lunar soil generically. And so you can calculate how many pinholes there ought to be. But the next chart shows the comparison of the prediction from optical density with the actual number of pinholes per square meter, per square centimeter. And it's 1,000 times fewer actually hit the Surveyor than should have based on the optical density. And when we do computer simulations of the ejecta, next chart, we can explain that because the simulations show the ejecta goes right over the top of the Surveyor. The Surveyor was down in a crater and the ejecta missed it. Next chart. That image we had at the top, at the beginning from Pat Rollins shows that the ejecta is a thin sheet, and on the left side you can see you can be under the sheet, and Surveyor was under it. So therefore, the damage should have been 1,000 times worse, which is pretty scary. Next chart. That's our best estimate. You know, there's a lot of uncertainty in this. So I don't have time to go through the details, but we've used optical density techniques to measure the amount of dust in every frame of these videos. Next chart shows we can do it by synthetically adding or subtracting dust to the images to match the statistical properties of the video frames. Next chart. And we've done, and that gives us an erosion rate equation for the lunar conditions. When we do terrestrial experiments, we get a different erosion rate equation. Next chart. But we do see there's a transition when you go from vacuum to rarefied conditions. And so we think that explains the difference in the two erosion equations. Next chart. And so this is the simplest theory that fits all the data. And we use this to predict how much soil is blown. Next chart. And I've got just a couple of seconds to say there's a haze that appears when the engine shuts off. After the engine shuts off, it suddenly appears. Takes about 20 seconds to decay. Next chart. By matching a let's skip to the next one. This is Ryan's data from her dissertation and other publications. And next chart, 5 seconds left. When we match velocities that are lower velocity, we can predict the decay of the haze, and it actually matches, by making it match the decay of the haze, it actually predicts the splash zone would be 75 meters radius. And so I think this is an effect of the engine shutting off, as the high pressure gas that was compressed into the regolith under the lander is allowed to decompress. It splashes dust with it that goes out at a much shorter distance than high-speed ejecta. So you're splashing a low-velocity blanket of dust around the lander, we think. Okay, that's all I've got. Top 2 questions. Number 1, how can we back out the effects of plume effects in our science? And number 2 is, how can we build the instruments and other assets to withstand the plume effects? Okay, that's it. Sorry I went over.